Hello, and welcome to the talk on energetic consistency in discretized models. I'm Roland, and this is part of the research training group course on math fundamentals. Today, we'll consider the Boussinesq equations, which are commonly used in atmospheric and oceanic modeling. They govern the velocity u and temperature T of a fluid and consist of the Navier-Stokes momentum equation for the velocity u, which includes a buoyancy force acting in the vertical direction, an energy equation for the temperature T, and an incompressibility condition on the velocity. The fluid is assumed to lie in a box, which is periodic in the horizontal directions, and the variables u and t satisfy the boundary conditions given here. The fluid is cooled from the top and heated from the bottom. And the non-dimensional parameters in this system are the Prandtl number, which is similar to the viscosity of the fluid, and the Rayleigh number, which can be thought of as the strength of the thermal forcing. I've got a simulation where the temperature is depicted using colors, red being hot and blue being cold, and the velocity is depicted using arrows. And the thermal forcing induces a flow in the box. Before we begin, we'll make some quick simplifications. We convert to a temperature variable theta by subtracting off a linear profile such that theta has zero boundary conditions. And in this variable, the equations become as follows. And for simplicity, we'll throw out the dependence on the second horizontal variable, although the results that we'll talk about today hold in 3D as well. Furthermore, we'll use the angle bracket notation to denote the volume integral. Now, the main topic for today is energetic consistency. If you take the momentum equation and compute the inner product with u, then you obtain the following equation. And by integrating by parts and using calculus, you can obtain the following kinetic energy balance equation. This says that the time derivative of the total kinetic energy for the fluid must obey this law, where we have a dissipative term and a thermal coupling term. In fact, the PDE must follow this the following balance equations for the kinetic energy, temperature variance, and potential energy. And so the first exercise is that you derive these equations by the procedure outlined above. And the question we're interested in is, do these same balance laws hold when we impose a discretization? The type of discretization we'll consider today is known as a spectral method or a Fourier series. So it's well known that any continuous function can be represented using an infinite series of sines and cosines. Here we sum over all possible wave numbers m, and for each m we have Fourier coefficients, one for each phase cosine or sine. And these sinusoidal functions are normalized by these factors of pi. In our problem, we have the following general Fourier expansions. The velocity field u can be written as a sum of sinusoidal vectors v, n, and theta can be written in terms of scalars fn. And the Fourier coefficients are indexed by bold n, which is a vector, since one can have two wave numbers, m1 and m3, in the horizontal and vertical, and a phase p. And the general formulas for these vector fields and scalars given the boundary conditions and divergence-free condition are given here. Now, from a computational perspective, we can only consider a finite expansion of u and theta. So rather than an infinite series over all possible wave numbers, we consider only a finite sum where the wave numbers that we choose are included in some index sets n sub theta, n sub u. These are written with a capital M superscript to denote that they're finite, and capital M will in some way denote the size of these index sets. Now, for a finite index set, we can define the corresponding projection operators, which are given by these formulas. And these projection operators, for instance, projection P sub u, acting on a vector field V, gives the best representation of V using the vector fields included in the index set NU. Now, we can't expect that a finite dimensional vector field like this one will solve the original problem, Navier-Stokes, because Navier-Stokes includes a energy cascade which trickles energy down from large scales to arbitrarily small scales. And so we can't expect that a finite dimensional field will satisfy this. But we can consider the truncated problem where we apply these projection operators to the right-hand sides. And these projection operators stop the energy cascade. So we could expect that a finite dimensional field solves this problem. The truncated problem can be converted to an ODE system where you recover the ODE by computing inner products. For instance, if we wanted to find the time derivative of the Fourier coefficient for an index n, we compute the inner product with the corresponding sinusoidal vector field. And in this way, you arrive at the following system of ODEs, one for each n which you include in your model. So to give an example, suppose we include only the largest scales of motion. So we have a one-dimensional velocity field and a coefficient which we've called large X. This only allows the fluid to circulate in large-scale motions. And we include two temperature fields. And if you do so, then by the procedure outlined above, you can obtain the Lorenz 63 system. And to give a simulation, we see that the Lorenz 63 system, as the trajectory is traced out, gives a fluid flow which allows for large-scale circulations, but nothing else. So it's just a coarse model. Now, we want to study energetic consistency in such spectral models. So to determine whether the spectral model satisfies the balance laws, we can use the truncated model to compute inner products. And it turns out that the kinetic energy and temperature variance are satisfied for any choice of your index sets nu and n theta. However, difficulties arise when you consider the potential energy equation. If you take the inner product that's needed for the potential energy balance, you get this. And by comparing with the terms that you see in the balance for the PDE, you find that the truncated model is energetically consistent if and only if this inner product of the linear profile with the projected nonlinear term is equal to this right-hand side. And this is not necessarily true. For the PDE, this projection operator is not here, and you can integrate by parts to get this right-hand side. But since this projection operator here is here, we can't necessarily do that. By doing some analysis in Fourier space, you can find that a truncated model is energetically consistent, and this left-hand side is equal to the right-hand side, if and only if the following mode selection criteria is satisfied. This criteria says that if you have a pair of indexes n prime belonging to n sub u and n double prime belonging to n sub theta, and they have equal horizontal wave number, which is positive, and equal phase, and if their vertical wave number is also equal, then you need to include twice the vertical wave number in the theta index set. It also says that if the vertical wave number is not equal, then you can only include you can only include the difference of their wave numbers if you also include the sum of their wave numbers. And now let's think about what's happening in the Lorenz equations. So here our index sets are 1, 1, 1 for u, and these two indexes for theta. And the criterion says that since 1, 1, 1 is included in both index sets, the criterion requires that twice the vertical wave number is included in n sub theta, and this checks out, so the Lorenz equations are energetically consistent. Now, as an exercise, I'll ask you to use the Fourier expansion to show that the left and right-hand sides of 6 are equal for the Lorenz model. And here you can use the following property, that the inner product of the linear profile with the projected nonlinearity is equal to the projection of the linear profile times the nonlinearity. This criteria allows us to build fluid models of arbitrary resolution. So if we want to include, we start here with the Lorenz model, and if we want to build more spatial resolution, then we can do so by the following process. We adjoin another mode, and the energetic consistency criteria requires that we also attach this mode of twice the vertical spatial resolution. And we can keep doing this and build higher order ordinary differential equations and get more realistic fluid flows. And we can do this to arbitrarily high resolution, always remaining energetically consistent. Now, a very important property that we found for energetically consistent models is that they always remain well-behaved. If you take the three balance laws um, described above, one for the kinetic energy, one for the temperature variance, and potential energy, and if you add them together in this way, then you get this uh, right-hand side. And after doing some manipulations, this right-hand side becomes as follows. And what we have here on the left-hand side is the time derivative of a norm of the variables u and theta. And on the right-hand side, you have a norm for u and theta as well, which is negative, and plus some positive constant. So what this says is that the time evolution of this norm on the left-hand side, it decreases always, since this is a negative quantity, until this negative quantity is balanced by the positive quantity rho. So that implies that solutions remain bounded for all time and the model is well behaved. And for the final exercise, I'll ask you to consider the energetic consistency criteria. Suppose we wanted to study a fluid model which includes the modes depicted here, which are given explicitly here. Then what would be the smallest extension of this model, which is energetically consistent? And for the final topic for today, we'll consider energetic inconsistency. So what happens if a model is chosen to be energetically inconsistent? As a case study, consider the Lorenz equations. If we throw out this mode, which saw was responsible for energetic consistency, the Lorenz equations reduce to this 2D system. And since this is a linear system, you can find the eigenvalues, which are given here. And in particular, for the Rayleigh number being greater than 1, this has a positive eigenvalue, and solutions will typically grow unboundedly at an exponential rate, which will very quickly lead to numerical blowup, where your solver will say, not a number. Now, we can prove that this same problem with numerical blowup will occur in a very large class of truncated models, which are energetically inconsistent. We hesitate to say that this always occurs for energetic inconsistent models, although it might be the case. But we can prove that it definitely occurs for uh, this naive choice of a box of Fourier modes where you just include every wave number up to some cutoff, where you can see that since the wave number 3, 3, for instance, is included for both, we should include twice the vertical wave number. And since this is not included, the same problem with Lorenz with, with finite time numerical blowup will occur for this model. Okay, if you want to see more information, you can use the following links, and that's it for today.